The three-phase full-bridge uncontrolled rectifier with pure resistor load has very high DC voltage ripples. In order to solve this issue, a filtering capacitor is usually connected on the DC side to suppress these ripples. Such a converter is called three-phase full-bridge uncontrolled rectifier with capacitive filtering. The operation principle for the three-phase full-bridge uncontrolled rectifier with capacitive filtering is similar to that of the one with the pure resistor load. Their diode statistics are determined by comparing the AC source voltage and the DC voltage. Note, as the filtering capacitor is connected on the DC bus, so the DC voltage is dynamically changed. So let's draw the waveforms together. At the beginning, the source voltage EAB is just larger than the DC voltage VDC. The diode D1 and D6 are turned on. Then the DC voltage equals to the AC source voltage EAB. The AC source is charging the capacitor and supply the current to the load. So the DC current IDC equals to the AC current until point A. At this point, the slope of the AC source voltage is larger than the slope of DC bus voltage, so the AC source voltage is lower than the DC voltage. All diodes are blocked. The capacitor is discharged to the load. There is no energy exchange between the AC side and the DC side, and the DC bus current is zero. Until point B, the new period starts. We can see the output voltage is smoother than that by the rectifier with pure resistor load. Under such a condition, the DC bus current is discontinuous. But let's think. There are some possibilities. For example, when the load is heavy, the diode will be conducting until next phase commutation. Then we can get such a waveform. The DC bus current is continuous, so what's the boundary condition for the DC bus current between the continuous mode and the discontinuous mode? The phase commutation point is the key point, which corresponds to the phase of 2/3 of the line voltage. If the line voltage slope equals to the DC voltage slope at this point, the diodes of the current phase are just blocked, and the diodes in the next phase are just turned on. This is the boundary condition. By deriving and solving the slope for the corresponding voltage, the analytical solution for the boundary condition can be obtained. It's omega RC equals the square root of 3. If omega RC is larger than the square root of 3, the DC bus current is discontinuous. And if omega RC is less than the square root of 3, the DC bus current is continuous. Okay, next let's use the Fourier series expansion to get the spectrum for the DC voltage. So besides the dominant DC component, the spectrum also contains the 6-case harmonics, such like 6th-order harmonics and 12th-order harmonics and so on. And the harmonic amplitude decreases with the frequency. And we can also see that comparing with the rectifier with pure resistor load, the harmonic amplitude and the voltage ripple are lower. Next, let's analyze the AC current spectrum. The harmonic distribution for the rectifier with capacitive filtering is similar to the one with the pure resistor load. The harmonic order is 6K plus 1 and 6K minus 1, such like 5th order, 7th order, 11th order, and 13th order, and so on. And their amplitudes are very high. The rectifier with capacitive filtering still suffers the serious power quality problem. When starting the rectifier with capacitive filtering, the initial capacitor voltage is 0. There will be large current surge into the diodes, which may damage the converter. In order to suppress the surge, inductors are usually connected on AC side. And this inductor can be used to suppress the current surge at the starting. It can also be used to smooth the current waveform. If the capacitor on the DC bus is small enough, then the grid inductance can be used to suppress the surge.